Hello and welcome to another exciting lecture for research methods. In this lecture, we're going to be talking about the correlational research strategy. The learning objectives for this lecture are to describe the goal of correlational research, to describe the directions, form, and strength of R, correlation, explain the 5 questions about correlation. Then we're going to look at regression and describe the goal of regression, and finish up with some about the third variable problem. So looking at explaining the third variable problem and then defining moderators and mediators. So the first learning objective here is describe the goal of correlational research. So we have to ask ourselves, what is our goal? Just like we've been talking about with all of these different types of research. And with correlational research, it's a bit different than any of the other ones we've talked about. Because the other one, you're either trying to do cause and effect, or you're trying to eliminate extraneous variables as much as possible with the different research designs. With this one, on the other hand, we're just trying to see if a relationship exists between variables. And if the relationship does exist, what is the nature of that relationship? So relationships can then be described but not explained. You can't explain why there's a relationship, but you can describe what the relationship is. And as I was basically just getting at, as a result, there's no attempt to manipulate, control, or interfere with the variables, just to see if those variables relate to each other. And the majority of the research that you're going to do until you get into more complex research is going to be just correlational. So when you're looking at giving a survey and just looking at if two of the variables are related to each other in that survey, what you're essentially looking at is correlation. You're looking at the correlational research strategy, the relationship between those variables. So again, just to reiterate that, experimental research, it does a good job of demonstrating that cause and effect. So the cause and effect between two variables. And if you've got cause and effect, those two variables are related to each other. But it's one variable that's related in such a way that it's causing a change in another variable. Correlational research is just seeing if there is a relationship between those two variables, and it doesn't determine cause and effect because of those things we've talked about, like temporal and control and all of those. Shouldn't be anything on this slide that's you don't already know, but when we're looking at correlation, we're looking at those two different variables. In this case, we've got an X and we've got a Y. And then you've got scores for each person, participant, company, city, whatever it is your identifier variable is. You've got two different values, one on each variable, one on X and one on Y. And you can plot them out as you see at the scatter graph down here, where you've got for individual A, they had an X of 1 and a Y of 3. And you do that for all of them. What you don't see here, but you'll eventually get, is you can have a regression line. That's the line of best fit that goes through them. But in a sense, what it comes down to is you've got, especially when you've got these interval and ratio level variables, where you've got them plotted out like this. You can actually do it for a categorical variable and a non-categorical variable as well. So at least one of your two variables has to be interval or ratio. So you can have one variable that's categorical, but you have to have one that's interval or ratio. If you've got both variables that are categorical, you do chi-squared, not correlation. But we've got these two variables here in this case, the section for a class and the score on a midterm. And when we look here, when you're looking at this section, we've got two different sections here in this case, and then the scores on the midterm for each of those. So you can do it in this way It doesn't look as clean as our scatter plot does before, but what you can end up doing is like this. When we're doing categorical variables like this, it does become more difficult if one of our levels of the categorical variable has more than 2 levels. If your categorical variable has only 2 levels, then you can easily do it like this. If it's got more than 2 levels, then which one do you put first, which one do you put last, and that makes it more difficult. But at 2 levels, we can do it like this, where you've got these 2 sections. Section it looks like 7 and section 11, and then you've got midterm scores for them. As I said already, down here is when you would do a chi-square when you've got 2 categorical variables. You can take this interval or ratio level variable here, this midterm score, and turn it into a categorical variable by separating them into categories. So let's say you do the cutoff at 70%, you've got it in here, and you have the number that fail and the number that succeed based on that. So this slide is stuff you've heard a few times this semester, and you're going to get that a lot in this set of slides, so that's why they're relatively short. But what does correlation do? Correlation is R. R is the Pearson product moment correlation coefficient, or R, the correlation coefficient. And basically what R does is it tells us direction, form, and consistency. The first of those is direction, and direction, you can have it as positive or negative. So if it's a positive number, if it's a number between 0 and 1, then it is basically as one variable increases, the other variable also increases, or as one variable decreases, the other variable also decreases. So the two variables go in the same direction. You can also have negative, and this is between -1 and 0. And this is the case where as one variable increases, the other variable decreases. Or again, the other way, as one variable decreases, the other variable increases. So where they do the opposite. The next is form. Now, to talk about this a little bit more than it's been talked about before this, you've got your standard correlational form here. And this is a linear relationship. So if you have a linear relationship between two variables, you've got where basically it's consistent throughout. As one variable increases, the other variable increases or decreases the exact same amount consistently throughout. However, there's also curvilinear. So our Pearson product moment correlation this is always going to be a linear relationship. However, you could have correlational relationships, a different type of correlation, but a correlational relationship where variables are related to each other, but they're not related in a linear way. Meaning, well, you see here early on in this, where we've got here, x is not increasing by that much, it's increasing a little bit, y is increasing a lot. But then as you get more towards the end, when you look at here, x increases a lot, but y is only increasing a little bit. So it's where the relationship isn't consistent. Now, for the most part in here, we're just going to talk about linear relationships. Most of statistics only talks about linear relationships. Curvilinear relationships are much more difficult to deal with. And then the final thing our correlational coefficient will tell us is the strength of the relationship. Again, we've got this between -1 and +1. And the closer the values are to the ends. So we've got this, we'll just do it here. We've got -1, 0, and +1. The farther you get away from 0, the stronger helps if I put all the letters in, the stronger the relationship. The closer you get to 0, the weaker the relationship. To the on the tails with the stronger relationship, if you get to -1 or +1, you have a perfect relationship. So it's the strongest or perfect relationship. If you get to 0, you have no relationship. When we're interpreting our correlation, we can, so you take the correlation, your R value, and you square it. You take R, you get R squared, and that R squared, it's always going to be a positive value. It's going to range from 0 to 1, and it is basically indexing the relationship between X and Y. It is telling you the percent of variability in one variable that's accounted for by the other variable. And when we evaluate it, when we interpret the strength, it depends on what field you're in. If you're in physics, any correlation that's below a 0.9 is going to be a poor correlation. Anything that's even below a 0.9598, you don't want anything that low. If you're talking about the behavioral sciences, though, in the behavioral sciences, we actually consider an R of 0.5, corresponding to that's an R squared of 0.25, to be a strong correlation. A moderate correlation is anything greater than R of 0.3 and an R squared of 0.09, and you've even got a weak correlation at an R of 0.1 and an R squared of 0.01. So just point out here that you can have these relationships and they can be weak or strong. It just all depends on the field you're in, on what these cutoffs are. Now, I would never test anyone on what these cutoffs are. These cutoffs that are in this thing here are pretty arbitrary, but it is a good rule of thumb used in the behavioral sciences. When we look here, you can look at this one up here. Well, what's the correlation here? Well, this is going to be less than 0.1, so it's going to be counted as basically no correlation. 0.09. Next one here, we've got a little bit stronger here. It looks like we got something going on here. So, yep, we've got an R of 0.21. It falls under this weak category. And then the final one, this looks pretty strong. We got a good strong one there. Yep, our R of 0.96, that's a strong correlation. And as I said before, how strong the correlation is does depend a lot on context. So if you're, let's say you're looking at an orchard and you pick many bags of apples, weigh the bags, then weigh them again. The correlation between the first and second weigh is 0.55. According to our guidelines, that's strong. However, that means your scale is pretty poor if between weighing them and then putting them down again and they're that much different that it's 0.55. If you're putting things on a scale, you expect your scale to have a correlation between two different weighings of the same thing of 0.95 or greater, if not even higher than that. A 0.55 correlation means you've got a pretty poor scale. You probably should look at your scale. Behavioral sciences, really different than that. But when we're talking about the physical sciences like this, it gets a little bit different. One of the other things we've talked about in here a little bit is effect size. So let's actually explain the 5 questions about correlations when it comes to effect size. So let's start by looking at when we talk about something like a strong correlation. Well, the stronger the correlation, the stronger the effect size. Meaning, if your relationship has a higher correlation, meaning when we look at, let's say we did a line of best fit here. You look at this bottom one, this B, and it's got a stronger correlation. Meaning, when we look at the distance of all of these lines, all of these dots from our correlation line, from our regression line, you see that the bottom one, they're basically closer to the line. So it is, because they're closer to the line, we're going to call that a stronger effect size because it's the correlation has a greater effect. And because of that stronger effect size then allows us to make more accurate predictions. If let's say we had a we're trying to see if this blue dot right here, how good of a prediction that is. Well, we can, and let's even just erase that and let's do something else. Let's say we've got a blue dot right here. How accurate is that? Well, they're both on the line. But when we look at the amount of variability that it could have, this one's going to have about this much variability. This one's going to have more. So this is the bottom one is more accurate. So stronger effect sizes then are more important, typically. Again, depends on your field. So all else being equal, a stronger effect size is more likely to be statistically significant if you're testing significance with your statistics, with your whatever stats you're doing. Let's look at that then. Let's look at if a correlation is statistically significant. So considering stats, considering the side of this that comes from stats, researchers are going to collect data from a sample and then make inferences about a population. That's how most of stats is done. And typically, the sample is going to mirror what's happening in the population. Sometimes it doesn't, and there isn't that association in the population. And just by chance, there's an association in the sample. What this is due to, and we'll talk about that in just a minute, what this is due to is error. Because if I collect a random sample from a population, there is a chance, a probability chance, that the sample I collect from the population is not representative of the population. Let's say I'm testing something and let's say age has an effect on it. And I test the population of everyone in the US, but I happen to get a random sample that's just people who are older. Well, then that error is going to affect my results. So we use statistical significance calculations based on probability, based on the probability that we're committing an error. We can never control it. So it's a probability estimate or p-value. If you take stats, or when you take stats, you'll get that. But p-value is a probability estimate, the probability of an error occurring. So when we do statistical significance testing, we set a threshold or a limit. Typically, that limit is 5%, and this is going to be our alpha. And we basically say that there's less than our alpha if our statistical results come out, our calculation comes out to it with our p-value of less than 0.05. That means there's less than a 5% chance that our results were due to error. And that's how significance testing works. Stats class will do more of that. Another thing that needs to be considered when we're doing correlation is outliers. Because could outliers be affecting this association between these two variables? Because outliers actually skew a correlation. And they can skew a correlation one way or another. Like for instance, let's look at this purple dot here. Purple dot here. What could be going on here? We could be looking at quiz average and midterms. And if we ignore that purple dot, we've got a pretty good correlation there. But what happened in this one right here, where this person did really poorly on the quizzes, but did really good on the midterm? It could be that they took quizzes and when they were bad on quizzes because they weren't prepared, but they really prepared on the exam. It could be that they didn't take the quizzes, and so their quiz average, they didn't take some of them, so they've got some missings. It could be they cheated on the exam. It could be a mistake made. The point is when you consider that in, our line of best fit, our regression line goes from something like this to something like this. It's basically pulling our correlation away from what it was. And that's the thing. Outliers, sometimes there's no explanation. Sometimes those might be legitimate. But anytime your correlation is strongly affected by an outlier, you should consider finding a way to toss the outlier. Looking at this here, uh, with this outlier, we've got a 0.37. Without the outlier, we've got a 0.26. Not that the correlation gets weaker without the outlier. Same with what we've got here. Correlation's actually pretty strong with the outlier. Without the outlier, it's really weak. So sometimes an outlier will make a correlation stronger. Sometimes it'll make it weaker. But the point is outliers mess with correlations, so you should consider not including them in your analysis. The next question, when it comes to of the 5 questions about correlations, is there a restriction of range? So restriction of range is going to be anytime there's not a full range of scores on one of the variables. So for instance, when you're looking at a good example here is looking at the graph and you look at GPA and SAT scores. So what is going on here is if you look at college grades based on SAT scores, what's going on here is a school that has an 1800 cutoff on SAT scores. And because of that, everyone has above 1800. So everybody has 1800 or higher. And you look at their GPA, and you've basically got a weak correlation between SAT scores and college GPA. Does that mean we shouldn't consider SAT scores on admissions? The issue here is that with this restriction of range, we are only looking at some of the SAT scores. If we actually admitted everyone to college, not looking at the SAT scores, admitted everyone, and then looked at their GPAs, and then compared them, you actually see that the relationship is a bit stronger, meaning that there is a relationship between SAT scores and college GPA. It's just not showing up, or it's weak here when you've got that restriction of range. And then the final question about correlations we have to ask is that correlation curvilinear? Or is that association curvilinear? And we talked about this enough already. Usually we do linear correlations, but if we graph it out and we look at this, we've actually got a curvilinear relationship. If we did a correlation coefficient R here, we'd have a very weak correlation. But there's actually a pretty strong relationship between these two variables. It's just not a linear one, it's a curvilinear one. And that's why you should always, whenever you're doing a correlation, you should always use a scatter plot. Scatter plot it out just to have a visual representation of it, because that scatter plot might reveal something like what you see here, something that you would not find if you just did your correlational analysis. Okay, let's shift gears and talk about regression. So the application of the correlational research strategy is regression. So again, correlation allows us to index the relationship between two variables. However, regression allows us to then take it one step farther and make predictions. So a correlational study demonstrates a relationship between the variables, allows us to use knowledge about that one variable to help predict a second variable. So in this case, even though we're not doing causation, we've now got a predictor variable and a criterion variable, a variable being predicted or explained. And we do this through the process of regression. It's the statistical process for using one variable to predict another variable, to find an equation that basically produces an accurate prediction of one variable if given a value of the other variable. So if given, in this case, the x is going to be the predictor variable. If you're given a value of x, you can then predict y from it, the predicted or criterion variable. So this gets us to the strengths and weaknesses of the correlation research strategy. First, the strengths, it helps describe the relationship between variables. Really good at describing a relationship. It's very non-intrusive. You can do natural behaviors. You can record people in their natural habitat. You can do surveys. You can do all of these different things. And it has very high external validity. However, there is also a lot of weaknesses. The main is you can't assess causality. In research, we want to assess causality. However, we cannot do that with correlational research. There is a long and complicated process where you can start to demonstrate causality with correlational research. When you do, you prove temporal, and you basically start controlling for, and you do everything you can to essentially create a research, a empirical research strategy without that, so you've still got the correlation. However, there's another big weakness of it, and that is the third variable problem. Just because two variables are related doesn't mean that there's a direct relationship between them, as we've said before. It could be a third unidentified variable that's responsible for producing the observed relationship, which we will start looking at in the next slide. There's a directionality problem. Again, it doesn't demonstrate cause and effect. So because of that, it could be the one you've got a predictor variable and a predicted variable. It could be the predicted variable is actually causing the predictor variable. So as a result, even though we've got high external validity, we've got low internal validity. And this gets us to our third variable problem. Looking at the third variable problem, what do we mean by a third variable problem? Let's look at ice cream sales and murder rate in New York. When we look at murder rate and ice cream sales, there's a really strong correlation between the two. This gets to the third variable problem though, because ice cream and murder rate are not directly related. They might be correlated, but they're not related in any direct way. One isn't causing the other. Changing one doesn't actually change the other. What we've actually got here is an effect of time of year. Temperature is another way to say it, but time of year. That is because during the summer, when it is warmer, crime rate is higher and people eat more ice cream. So during the winter, when people are staying inside, crime rate's lower, ice cream sales are lower. So you've got this almost perfect correlation between crime rate and ice cream sales. However, they have nothing to do with each other. They actually both have to do with a third variable, which is either time of year or temperature. So when we've got more than two variables, what we end up doing is what's referred to as multiple regression. So multiple regression, it's a statistical procedure in which we basically look at multiple different variables at once, and we can then examine the relationship between two variables while we are controlling for another variable. We are essentially controlling for those confounding variables. And what ends up happening then, we're still only describing a relationship, we're not explaining it, but we are ruling out potential third variables. And one of the things you can actually get with multiple regression is when you find another variable that does influence your relationship between the two. So you've got those two variables, these two specific variables. You find a variable that influences this relationship. Multiple regression can actually help you explain how that third variable influences that relationship between the two. So we're looking at it. So we've got a bivariate correlational study of amount of daily recess time and the level of behavioral problems. These two variables are found to be negatively correlated. Not that strongly negatively correlated, but negatively correlated, so that as recess time increases, behavioral time decreases. But they also measured a whole bunch of other variables along with this, and looking at things like proportion of children eligible for free lunch, number of students in the classroom, public or private schools. So the researchers were able to conduct a multivariate correlational study by then going in and looking at to see if any of these other variables are actually explaining this relationship between them. The initial argument here is trying to say that the more recess students have, the less behavioral problems they have. The problem here is, though, because it's correlation, we can't say that this is a direct relationship. It could be some other variable. So by measuring these other variables, looking at eligible for free lunch. What does that mean? That's going to be something like income, because or SES, social economic status. Children who are eligible for free lunch typically come from lower income families. Number of students in the classroom, that could have a big effect. Public or private school, again, income, you've got an effect. So because we're able to look at this multivariate study, we're now able to look at to see if other variables are causing this relationship between behavioral problems and recess. So we look at income. So controlling for the variable, meaning holding it constant. So we look at all of these different relationships now, but now let me do 3 different colors here. It looks like we've got a red is, we're going to look at low income. So look at the dollar signs. So $1 sign, low income. So we look here, we've got a line about like that. Let's change it to blue. So we've got blue with $2 signs, medium income. Looking here, we've got somewhat of a relationship, but it's a weaker relationship. Let's even go now to orange. And we've got $3 signs here. We've got high income. And we look here, and there looks to be a relationship, but it looks to be weaker. Maybe I could have put that a little bit steeper of an incline. But the point is when we look at this, we see that there's actually an effect of income on this relationship between behavioral problems and minutes for recess. So it could be that more likely that poorer children are more likely to have behavioral problems and more likely to be in schools with less recess as a result. So these 3 variables are correlated with the other 2. The researchers here want to know whether income, the third variable, can explain or account for the relationship between them. To answer this, they'll need to see what happens in the relationship between recess and behavior when controlling for income. Meaning, they do it like I did here, where they've got a different regression line for each of these different income levels. And by controlling for it, and you control for it with multivariate regression with your statistical program, SPSS, SAS, Excel, any of these, and you can actually start to find out if these third variables, like income, actually have an effect on this relationship between the two, such that that income is actually causing the relationship between to be present in some cases and not in others. Which leads us to moderators and mediators. These two are hard to differentiate. People get them confused all the time, but moderators are going to be when a relationship is only present under some conditions. So that one on the previous slide, where the relationship was only present, really, it was present under all conditions, but it was much stronger under some conditions. So in this case, the relationship is we'll even say the one wasn't significant for high income. That means it's the association between recess and behavioral problems is only present for those that medium and low income. So in this case over here, we've got gender moderates the relationship between extroversion and group conversations. So we've got this relationship. The relationship is present between extroversion and group conversations. However, someone tested it and studied and found that gender actually affects this relationship between extroversion and group conversation, such that only in female individuals was, erase that, covered it up. Only in female individuals was the relationship significant. It was not significant in male individuals. So in males, there is no relationship. There is no correlation between extroversion and group conversations. In females, there is a relationship or a correlation between extroversion and group conversations. So that makes gender a moderator in this case. So gender moderates the association between extroversion and group conversations. The example I've used before, bussing tables and chicken wing consumption. That people eat more chicken wings when their tables are bussed. There's a correlation between chicken wing consumption and bus tables. So there's a correlation between the two of these. However, it only happens in distracting environments. So if there's a distraction, there's a relationship. No distraction, there's no relationship. So distraction or the environment moderates the association between bussing tables and chicken wing consumption. If there are moderators, this suggests that the relationship has limited external validity because the moderator is actually what's causing this effect. The relationship could still be very important within a particular group or situation, but not in all contexts. So one of my papers I described in here before as a undergrad, I published a paper basically on the relationship. So going back a few steps, Justin Carre is a researcher who had found a relationship between facial width to height ratio in hockey players and their penalty minutes, measure of aggression. So he basically said there's a relationship between facial width to height ratio, which is a measure of masculinity, and aggression. But he only measured some hockey teams. As an undergrad, I measured all hockey teams, and the finding went away. And it turns out that there's been mixed findings when you look at various different studies that have been done. There was mixed findings. Some found a relationship between facial width to height ratio and aggression, and some didn't. So the question became, what is going on here? Why is this relationship present sometimes and not others? Well, when I got to grad school, Justin he started working at that same grad school that I went to, and I started working with him, and we looked at this problem. We looked at this relationship, and we tried to find out if there was a moderator to this relationship. And what we actually found was social status moderated this relationship, such that those who were high social status, high relative social status to their peers, they did not have the relationship did not exist between facial width to height and aggression. Those that were low social status, though, there was a relationship between facial width to height and aggression. So in that case, basically the logic behind it is those who are lower social status subjectively had more to lose, so they could be aggressive, but then who was aggressive? Those who were more masculine, those who had the ability to win aggressive conflicts. Whereas even in those who are high social status, even those who have the ability to win aggressive conflicts, they have more to lose by being aggressive, so they're not aggressive. So finding moderators is very important to research. Which gets us to the other one, which is mediators. So a mediator, defining mediators, a mediator is basically why two variables are related. It's looking at the why of the relation rather than the when of relation. better way to look at it is moderator determines when the relationship is present. A mediator determines it's a third variable that explains why the variables are related. So looking at it explains the how or why of the relationship between variables. Once scientists have then established the causal connection between the two variables, they can then attempt to identify any mechanisms involved intermediately. So again, here we've got this relationship between recess and behavioral problems. And we know that this relationship is present. If the relationship is present and we've eliminated all moderators, and we don't even have to eliminate all moderators, but we can statistically test for mediators, one thing we want to do is test for a mediator. And a mediator is going to be something that explains it. So it could be that in this case, that more recess means more physical activity. More physical activity then means less behavioral problems. It isn't the availability of recess that's directly reducing the behavioral problems, it's the physical activity that comes with it. And how could you test this? Well, you can test this by controlling for physical activity. Testing kids who are more physically active during recess and those who are less physically active, and seeing if in those who are more physically active, if it then reduces behavioral problems more than those who are less physically active. In that case, then you've identified a mediator. In that case, the possible mediator would be that physical activity is mediating that relationship between recess and behavioral problems. So how would we do this? With correlational data, we go through 5 steps to test mediation. First step, we test for the relationship between our two main variables. In this case, we're testing C. We're testing to see if there's a relationship between availability of recess and behavioral problems. Now, the old rule used to be that there had to be a relationship between these two variables for a mediator to be present. There's actually a new rule now that the relationship between, in this case, recess and behavioral problems does not have to be significant to find a mediator, but there has to be some type of association. Then we're going to test for the relationship between availability of recess and physical activity. There has to be a relationship between these two variables for us to have physical activity as a mediator. If there's no relationship between recess and physical activity, then it's not a mediator here. Then we test for the relationship between behavioral activity and physical problems. Behavioral problems and physical activity, sorry. And this activity and problems, if there's no relationship here, we don't have a mediator. But if there is a relationship here, we've found a relationship between recess and problems, we found the relationship between recess and activity, and we found the relationship between activity and problems. Now we run regressional analysis, and we need to see if, using physical activity and recess as predictor variables, to determine if this relationship goes away once we've accounted for this relationship here. And once we've accounted for recess, physical activity to behavioral problems, once we've accounted for that statistically, if this relationship goes away, then we now know, or if it gets weaker, now it doesn't have to just go away anymore. If it gets weaker, we now know that this physical activity is a mediator of recess and behavioral problems association. And finally, we have to do temporal precedence. We have to show that this comes before this, comes before this. Specifically, the first variable followed by the mediator, followed by the outcome variable. If we have temporal precedence, then we can say that there is a relationship between these, and it is a mediated relationship. The physical activity is a mediator. And this gets to our basically looking at it in a graph form. First, mediation. Why are the two variables related? They're related because of a third variable. Another example, viewing violent TV is correlated with aggressive behavior. Why? It could be that we could find the mediator, that we become desensitized to violence. Moderator, when is a relationship present? So we've got the relationship between two variables, but the relationship is present or stronger in one group than another. So in this case, we get viewing violent TV and aggressive behavior. And let's say we're looking at one type of, we're looking at boys and girls here, that the relationship is present for boys, but not present for girls. And then finally, you can just have a third variable, but that's not a mediator or a moderator. A third variable that in the sense A and B are related to each other, but they're only related to each other because of C, because of this third variable. So let's say the third variable that viewing violent TV and aggressive behavior are not actually directly related. They're only related in the sense that having lenient parents leads to both. So these are three different types of third variables that can affect relationships between or correlations between two variables. All right, that ended up a little bit longer than I intended, but we described the goal of correlational research. We looked at describing the direction, form, and strength of R, the 5 questions about correlation, the goal of regression. Then we looked at the third variable problem, and we looked at mediators and moderators. Thanks. Come on back.